Welcome, IB chemistry students, HL Chem. How are you guys doing? It's your HL chemistry teacher, Mr. Kenton, and wanted to put together for you guys some stuff on electrochemistry, as we talked about in class, because I feel like this is a topic that probably got glossed over in AP chemistry, not because I was intentionally trying to gloss over it, but because we were running out of time. And it's also just an important topic to just want to know more about. And I think it's interesting. And so hopefully you'll find this useful. And so today we're going to be talking about oxidation reduction reactions, which are also commonly referred to as redox reactions. So with that, let's just take a look at what exactly is oxidation reduction and how do we determine that and what type of reactions fall in that category. Okay, now the chapters that are listed there, that corresponds to the Brown and LeMay textbook. It does not correspond to our IB textbook. I'll try to get you guys some more information about the IB textbook on Google Classroom. Okay, so oxidation reduction reactions. So an oxidation reduction reaction or redox reaction is where one or more electrons are being transferred from one species or one substance to another. Okay, and if you remember when we talk about chemical reactions, it generally boils down to precipitate being formed, gas being produced, energy being transferred or changed, and electrons moving. And so this is focusing in on those electrons moving. Now, for chemists, in order to keep track of these electrons, what they came up with is this thing called an oxidation number. So chemists use oxidation numbers. Now, like in almost everything in chemistry, oxidation number has multiple meanings. And so the first meaning is if we're dealing with a monatomic ion, so something like sodium ion, it has a 1+ charge. Well, we could also say that that would be its oxidation state or its oxidation number as well. Now, the second way that we can use this is that we can say that it is the hypothetical charge that's being assigned to an element within a bond based on an assigned set of rules that chemists have agreed upon. Okay, now with that second function, it's going to be a little bit different than just simply the charge. Okay, and we'll look at that much more in depth as we move forward. Now, in an oxidation reduction reaction, the electrons are always going to move from a substance that is being oxidized to a substance that is being reduced. Now, you might be thinking to yourself, that's great, Mr. Kenton, but what does it mean for something to be oxidized and reduced? Well, oxidation from a chemistry perspective is going to be the loss of electrons. Okay, so anytime a substance in a chemical process is losing electrons, we would say that that substance is being oxidized. Okay, and if you look at the example that I've given you here, you've got lithium that's then being oxidized. It's losing an electron, and it's forming that lithium plus ion. Okay, and so in that particular case, that would be the oxidation of lithium. Now, reduction is the gain of electrons. So when one of those substances, like in this case, when lithium loses an electron, in a chemical process, some other substance has to gain the electrons that substance lost. And so reduction is going to be the gain of electrons. And here we have the example, you've got 2 Fe3+. It's going to gain 2 electrons, and it's going to be converted to a 2 Fe2+ ions. So it changes from a +3 charge to a +2 charge, or a 2+ charge, okay? And a good mnemonic to help you remember what's oxidized and what's reduced is oil rig. Oxidation is loss, and rig, reduction is gain. If you don't like oil rigs, if you're trying to be environmentally conscious and environmentally friendly, you can go with Leo the lion goes grr, right? Leo, loss of electrons, oxidized, goes grr, grr, gain electrons, reduced. So you got oil rig and you got Leo the lion goes grr. Whichever one can help you remember and help you kind of separate out those two, use that. I think it's helpful. I've used it. My high school chemistry teacher shared that with me, and here I am passing it on to you. So hopefully it continues. All right, so that's oxidation reduction reactions in a nutshell. So let's now take a look at these oxidation numbers and what are these sets of rules that chemists use to be able to assign oxidation numbers. Okay, so here are those rules. So the first thing that we want to look at is that if it's an atom and it's in its elemental form. So if it's being formed, like you're taking the elemental form of it, pure substance, like sodium. Sodium's a solid. Its elemental form, its oxidation number is always going to be 0. Okay. If we have diatomic hydrogen, that's a gas. That's the natural occurring form of hydrogen. It's going to have an oxidation number of 0. Okay. So pure elements, pure substances like that, going to have oxidation numbers of 0. Okay. Second thing that we want to keep in mind, if in your balanced equation you've got a monoatomic ion, that means that the oxidation number of that particular ion is going to be equal to the charge. Okay, so if you've got Na plus, or if you've got Cl minus, Na is going to have a +1 oxidation state. Chlorine in that particular case, or chloride, would have a 1 minus, or a -1 oxidation state. Okay, now where we start to see some deviation here is when we start looking at the nonmetals. Okay, so nonmetals are usually going to have negative oxidation numbers. Okay, very similar to their charges, but with some slight deviations. Here are some things that we need to consider. Oxygen is going to always be -2 for its oxidation state, unless it's in peroxide. Now, if it's in peroxide, it's going to be -1. So like in H2O2, the reason why that compound forms based on oxidation is the fact that each oxygen is going to have a -1 oxidation state. Hydrogen can be kind of unique. When it's bonded to nonmetals, hydrogen takes on a +1 oxidation state. But when it's bonded with metals, like sodium hydride, NaH, it's going to have that -1 oxidation state. So hydrogen can be +1 or -1, depending on what it's attached to. If it's bonded to nonmetals, +1. If it's bonded to a metal, it's going to be -1. Okay. The oxidation number of fluorine in all compounds is -1. Okay, so that fluorine rule trumps everything else that's there. So that means if oxygen and fluorine are bonded together, fluorine is going to have a -1, which means, newsflash, spoiler, oxygen would have a positive oxidation state, which is crazy. That doesn't even make sense. But it does, because chemistry, oxidation numbers make it happen. Okay. Now, when you're dealing with a compound, if it has a neutral charge, right, you look at the chemical formula and there's no positive or negative charge associated with that substance, then the sum of the oxidation numbers of all of the atoms in that compound have to add up to 0, right? If you've got something like a polyatomic ion, for example, like take nitrate, for example, NO3 1-, then the sum of the oxidation numbers in that nitrate ion need to add up to equal the charge on the ion. So when you look at NO3 1-, if we use those rules, oxygen would be -2 there. You've got 3 of them, so that's -6. It has a -1 charge overall. That means that nitrogen in that case would have a +5 oxidation state. Okay, and so that +5 -6 gives us that -1 charge, which matches up with what we've got. Now, as I'm saying that, please keep in mind that oxidation number does not mean charge, okay? It's that set of rules that we're using to assign what's going on with the electrons in a given molecule, okay? And it's a bookkeeping method that chemists use to help track this idea of oxidation and reduction, okay? Now, the neat thing about oxidation and reduction reactions is that they're so diverse, okay? And pretty much almost all of our reaction types can be classified as a redox reaction. Your combination reaction, so synthesis, that's going to be a redox reaction. Your decomposition reactions, those are going to be redox reactions. Combustion reactions, those are going to be redox reactions, okay? And so that's kind of the neat thing here. So just kind of keep that in mind, that lots of different reactions are actually part of this bigger category of oxidation and reduction. Now, the other major category that we see with oxidation and reduction is going to be single replacement reactions. Okay, so you've got an element replacing another element in a compound, then you get the formation of a new compound and a new element, right? And so, like in the example there, you've got potassium reacting with water to form potassium hydroxide and hydrogen gas. Now, if you want to go through and kind of assign those rules, talking about those oxidation states, in potassium, because it's in its elemental state, then its oxidation number would be 0, right? Now, over here, you've got your H2O. You've got oxygen, so it's going to take on a -2 oxidation state. You've got hydrogen. It's bonded to a nonmetal. That means each of those hydrogens has a +1 oxidation state. If you come over here and you're looking at potassium hydroxide, the potassium, it's going to form, like it can break apart, it's going to form K+ ions, so the oxidation state for the potassium here is +1. The oxidation state for the oxygen here is -2, because it's paired up with that hydroxide. So OH-, so you've got the -2, the hydrogen's +1. And then this hydrogen gas here is going to have an oxidation state of 0 because it's in its elemental form. Okay, so that's just even practice with assigning those oxidation numbers. Now, with single replacement reactions as a whole, they usually contain an element that replaces another element in aqueous solutions. That means when it's been dissolved in water. Now, a good rule of thumb, your metals will always replace other metals. Notice here that the potassium replaced, I'm going to say, the positive substance H from water to get potassium hydroxide. Notice that the potassium did not replace the oxygen. Okay, your halogens, so your elements that are in group 17 or 7A, are going to be able to replace other halogens. And the last thing to keep in mind is that chemists use the activity series to help determine whether or not chemical reactions will take place that are single replacement reactions. Now, that's going to have even deeper ties into oxidation and reduction when we look a little bit later on. When we start talking about the spontaneity and the energetics that go behind this, which we're going to get there, we're not there yet, but just kind of keep that in the back of your mind. And so if you remember the activity series, now you have to bear with me, I'm going to have to move my face here. Hopefully that's not weird. All right, so you got the activity series that's there, it looks something like that. And the activity series is just meant to show you whether or not metals can replace other metals, right? And ultimately, when we think about this in terms of oxidation and reduction, the activity series actually shows us how readily one metal can be oxidized as opposed to another. And so if you're looking at the diagram, it's telling you that as we move up, it is much easier for lithium, for example, to lose an electron as opposed to something like gold down here that's having to lose those 3 electrons. Okay, so the higher up it is on the activity series, the more readily it's willing to lose electrons and become an ion. And that should make sense to us, right? So that just gives us a little bit of information about activity series and how that plays into our single replacement reactions and what it actually tells us about oxidation. All right, now balancing redox reactions. So this is where things get a little interesting. Now I moved my screen a little bit. Sorry about that. This is where things get a little interesting because when we talk about balancing equations, we think of just typically changing coefficients and making sure that we have the same number of atoms on both sides. But when it comes to redox reactions, it's actually a little bit different. Okay, so we have to consider 2 things when we're looking at redox reactions. The first thing that we have to consider is conservation of mass, just like in any regular chemical equation we're dealing with. The amount of each element present at the beginning and end of the reaction must be the same. If you started off with 2 hydrogens, you better end with 2 hydrogens, right? But now we have to consider what's going to happen with the charge, because we're looking at the movement of electrons, so charges are changing. So we have to obey the law of conservation of charge, and that means the number of electrons lost by one substance has to be gained by another at the end of this particular process. Okay? And something that chemists do is they break a reaction down into 2 halves. They break it down into the portion of the reaction that's being oxidized, and they break it down into the portion of the reaction that's being reduced, so they can deal with that mass and charge component, and then they combine the 2 half reactions to get the overall balanced redox reaction. Okay, and my plan, ladies and gentlemen, is I'm going to produce a second video that's going to have me working out an example of actually balancing a redox reaction. So we'll be able to walk through that together. Okay, so if you're like, Mr. Kenton, I don't remember how to do that, that's okay. I'm going to address that. All right, and so again, those half reactions, it's a convenient way. It allows chemists to kind of focus in on the changes in mass and charge for the oxidized and the reduction portion of the reaction. All right, so here are our rules for dealing with balancing redox reactions. Oh, I moved my screen again. Thanks for bearing with me in my technology. Okay, so I'm moving it so you can see everything. So in order to balance a redox reaction, it's typically going to be carried out in acidic solution, but it could be in basic solution, and I'm going to talk about how we deal with both of those. But look, right now we're going to look at acidic solution. So your first task is going to simply be to dividing your equation into those 2 half reactions. You're going to look for the substance that's oxidized, and you're going to look for the substance that's reduced. Okay, and so what you'll have to do is you'll have to assign oxidation numbers to all of your components in your reaction, and then use oil rig or Leo the Lion says grr to identify what was oxidized and what was reduced. Okay, once you've done that, what you're going to do is you are going to balance each half reaction by the following steps. The first thing you're going to do is you're going to balance the elements other than H and O that are present in your chemical equation. Okay, so you start with kind of the things that are going to be easiest to balance. Okay, you can use just regular coefficients to do that. Now here's where things start to change. So once we've balanced our other elements that are present, what we're going to do is, in order to balance oxygen, what we're going to do is we're going to add water molecules to the side where we need to have more oxygens. Okay, so to balance oxygen, you add water. All right, now once you've balanced out your oxygens, you're going to add hydrogen atoms, balance hydrogen atoms by adding H plus ions. Now, the H plus ions is coming from the fact that it's an acidic solution. So you're using a strong acid, you get a bunch of H plus ions that completely dissociate, and so you've got H plus that's present. That's where the H plus is coming from. So that's how you balance out H. Now, those first 3 steps deal with the mass component, so dealing with the mass. The last thing that you're going to need to do is you're going to need to balance the charge by adding electrons to the side with the greater overall positive charge. And you can also think of it in terms of whatever process that you did, right? So, because you want ultimately your charges to balance out. Now, again, when we look at an example, that'll make a little bit more sense. Now, once you do that, you're going to multiply each half reaction by an integer so that the number of electrons lost in one reaction equals the number gained in the other half reaction. That's that conservation of charge piece. We can't forget that. Okay. Once you've done that, you're going to add your 2 half reactions together, and you're going to start simplifying. You might have too many water molecules on one side, or maybe they're showing up on both sides, and so you're able to cancel something out. Maybe you're going to have H pluses that are on both sides, but then they cancel out, so that you have a certain number left over. And you're going to keep doing that until you've canceled out everything and it's simplified. Excuse me. And then lastly, you're going to check your equation to make sure that there's the same number of atoms of each kind and the same total charge on both sides. And if you meet those criteria, then congratulations, you have balanced a redox reaction. Now, you might be thinking to yourself, Mr. Kenton, that's a lot of steps, and I haven't done this in a while. like I said, I'm going to be posting another video of us going through this, and so you can see this as an example. Okay. Now, that was for acidic. If you're in basic solution, it's pretty straightforward. You follow the same steps that are on the previous slide, but what you're going to have to do at the end is you're going to have to remove those H pluses because it's not acidic, it's basic. And so what you're going to do is you're going to add hydroxides to remove H pluses, which means you get more waters. You cancel out additional waters, balance it accordingly, and then you're done, right? And so, that's how we balance redox reactions. So for you guys, here's what I'd like for you to do, right? You've got these reactions. I want you to identify the oxidation reduction half reaction, balance each of them using those rules, and come up with your balanced redox reaction. All right. So thank you guys for stopping in.